seconds.
Less than a minute. All right.
Okay, so hello everybody. This is the Prague seminar for mathematical physics. Today we are resuming with the talk delivered by Vincenzo last week, and more specifically, he will likely finish his topic about T-duality and Courant algebroid relations. And because everyone already knows Vincenzo, there is not more to say. So my job is a bit easier today, and it remains just to wish you enjoy the show and let Vincenzo's words sound.
Cheers, thanks. Well then, I guess first of all I have to rectify some wrongdoing that I've done like last time, which is I didn't mention that this is an ongoing work with my collaborators. Yeah, funded by and Vincenzo. I think it could have been good to mention their name at some point, but anyways, we are my friends. And yeah, and maybe I just didn't reference enough people like who have been contributing to the group, so they're kind of all like well-known people. It's just pointless for me to stress enough how important their work was. But yeah, anyways, last time I tried to introduce you to the notion of Courant algebroid relations, try to use them or like show you an example of a Courant algebroid relation that comes from isotropic production of exact Courant algebroids over foliated matrices. That's the bottom line. So I named the relation coming from the reduction procedure Q of K, where K is a isotropic subbundle that turns out to be involutive because of the conditions we assume, i.e. the importance of basic sections spanning the K pair. So the perpendicular of this bundle of our Courant algebroid E, sorry. And yeah, this is just a relation from an exact Courant algebroid E over basically for them to here. So an exact Courant algebroid over, this is going to be over Q, that is M of F, where F is a foliation of M induced by K, and this is just going to be Courant algebroid over M. Actually, this relation, I also told you, it's not just a simple relation. According to Jan's paper, I should be more careful with these arrows. We draw it like this. Because this relation, which is the subbundle of the product Courant algebroid with some choices of sign for the inner product and the product, is actually supported in a submanifold that is given by the graph of this surjective subversion here. Okay, so QK is supported on the graph of omega, which is clearly a submanifold of M cross Q. Okay. One more notion I will need in the future is actually how to take the transpose of this relation, which is going to be denoted by QK. Is actually this big enough or still too small? Huh? I don't know. I'm not very good at this deciding the size. So how do you take the transpose? Well, the transpose is actually pretty much given by QK itself, but you can just see it as a subbundle, so an isotropic involutive subbundle that has some properties like with respect to the anchor of our product from algebroid. You can see this as a subbundle of E red cross E bar, which this bar just means like that you're taking the opposite inner product with the different sign. The only problem is that this is not going to be a relation supported on, well, it's still going to be supported on the graph of pi, but you cannot see it as a graph of a map from Q to M because pi is clearly not invertible. So in this case, I should actually write that Q a transpose is actually just a relation from E red with this notation. So no graph of omega, even though the submanifold of M cross Q is just the same. But yeah, you cannot just see it as a graph of a map from Q from Q to M. I will need this in the future for, well, no spoilers for now. So this was something I told you in the previous episode. Then I also wanted to stress that I want to recall the definition of generalized metric, which at least for a Courant algebroid is just given by a subbundle B plus of E, which is maximally positive definite with respect to the inner product. Okay, so if E is an exact Courant algebroid, the rank of V plus it will just be the half of the rank of E. Okay. And one more thing I told you is like when a relation is actually generalized isometry for generalized matrix. Okay. Let me recall this definition. In particular, I can for two. Okay, so let's take E1. Let's take two generalized metrics, E1 plus recurrent algebraic E1 and B2 plus recurrent algebraic E2, respectively over M1 and M2, and a relation R to E. So R is a generalized isometry if the following happens: supported on C, which is a submanifold of say M1 plus M2. If the following happens, so R is a generalized isometry if for any P in C, we have the R at P actually equals to R of P intersection curly V plus direct sum R of P intersection curly V minus, where curly V plus is simply the subbundle of E1 cross E2, but E1 cross E2 bar over line given by V1 plus V2 plus, and V minus, well, it's just going to be given by the same thing, where where's V minus, well, where V1 minus is just V, well, let's say VI minus with VI plus orthogonal, which is going to be, again, negative definite with respect to the inner product of algebroids, but then again, it sums up to giving like a generalized metric. So this is the definition that I want to generalize, because I told you last time that if you consider a relation between for a reduction procedure, pretty much, and you have an isotropic, let me stress, isotropic reduction procedure, this relation is not going to be a generalized isometry. Okay, it just doesn't happen, and the problem is that the reduction is isotropic. Let me stress that. Actually, Jan provided an example in which QK for a G-equivalent reduction of Courant algebroids is, I mean, actually give like necessary conditions for them to be an isometry, but you have to give up on something. And in a specific case, you have to give up on the fact that the reduction is isotropic. Actually, a necessary condition would be that K intersected K per is actually 0 for this guy to be a generalized isometry. And my point of view here is that I want to keep on going, but preserving the isotropicity of the reduction. So since I cannot have everything in life, I have to give up on something else for QK to be something somewhat of an isometry. Okay, and so the thing that I'm going to do in order to show that QK can be some sort of isometry, not really a generalized isometry, is change the definition of generalized metric. So give what I told you last time, introduce a different object that was defined by Chevera and Stroll, that is called transverse generalized isometry, and define a notion of isometry for this. I don't want to say much, but for this different object, okay, which allows for some sort of more degree of freedom. Because I think last time I told you that pretty much the problem with QK is that when you do the whole reduction procedure, you have a natural map from a perp to the reduced Courant algebroid over this surjective submersion, covering the surjective submersion. And the problem for QK not being a generalized isometry is that pretty much the kernel of this map, sharp, is non-trivial. It's actually defined by K pretty much, which also kind of justifies why you want something like that when you want to change a little bit the problem. Like when you want to introduce, when you want QK to be a generalized isometry. So yeah, I'm going to try to introduce a notion of metric that allows for more degeneracy and actually has K inside it, so that you can actually probably try to get around of this problem using this notion. So I actually already told you about this definition, which is given by, say, K what is a K transverse generalized metric for an exact Courant algebroid E is again, if we can guess, it's subbundle of E, whose rank is again maximal in some sense. And you also impose some other conditions. First and foremost, K actually sits inside W, which again sits inside K pep. And you also impose that the inner product for your Courant algebroid for any element okay, so for any element W that is not in K, this must be positive definite. So everything outside of K is well behaved, pretty much. That resembles exactly what you have when you define this, but it's allowing for some sort of degeneracy, right? So you have, if you want to compare it with this definition, B plus has the same rank, but it doesn't allow for any element to have zero inner product. This one does, potentially. And there are all the elements in K, okay? And one more in where does transversality comes into play is just that we're going to impose an invariance condition with respect to K of this structure, which is just given by every section of W. This bracket is again going to be a section of K. And I also told you last time that this is not like a this is not just showing up randomly, because if you actually have a subbundle of an exact Courant algebroid that can be reduced, whose intersection with K has with K verb as constant rank and satisfies this condition, then it means that it can be reduced to irregular. So it will become a subbundle of irregular. This is a result due very much to Michael Zamboni, if you can find it in some of these papers. And you actually end up having one more interesting condition, is that if this happens, you can also find out that W will be spanned by pointwise spanned by basic sections, okay? Which were those sort of kind of special sections that I introduced to you last time, okay? So once I have this, I can pretty much introduce my new notion of isometry, okay? If you want an example for this, you might think of exact Courant algebroids, or well, let's say split Courant algebroids, so Tm direct sum T star n over Riemannian fourier manifolds. So you have a metric G M endowed with the metric that is not really a metric, is just it's symmetric, bilinear, constant rank, but is not degenerate. It has constant rank, but is degenerate. And the point is that the kernel of G actually the manifold is actually given by EF. This object here is exactly a special example of W, okay? In which your W is pretty much going to be given by the graph. And as you can see in this graph, TF is sitting inside W, and TF is pretty much equivalent to a choice of K, and K perp is going to be again Tm direct sum the annihilator of Tf, which clearly contains this guy. So this would be an example for these objects. Okay. Okay. Well, enough chit chat, and say I'll try to give you now an example. I'll try to give you the definition of what I would call a transverse generalized isometry. Okay. Let's try this technology here. Let's evolve. Okay. So, what kind of object do I want to preserve now? As you've seen, only the bit that is not only the bit of W that is not in K actually represents some sort of tensor. Let's put it that way. It represents some sort of structure that might happen in general B, okay? Apart from the invariance condition with respect to that, which would tantamount very much to that B plus subbundle. So what I would like to do is actually to find a subbundle of W that is kind of similar to B plus, let's put it that way in our interpretation, that can be preserved, and not restricting necessarily to objects that also preserve K, because that might be a bit too restrictive. And well, in particular, if you want to study T-duality, you'll end up showing you that you just have no, you just preserve all the topology for all the manifolds you want. Or like, I think, well, I'll talk about this like in more detail later. So in particular, what do I want to do? Consider, for instance, like, short exact sequence associated with W is just given by the obvious. I will define my isometry by choosing S, which is going to be a splitting of the short exact sequence. Well, not choosing, but defining it if in case it exists something like that. That satisfies. So I'm gonna, for future notation, I'm gonna call W tilde plus with some numbers, maybe even just the image of this. Okay, this is just for purpose of notation. So let me give you the definition right away. So
Just 1 second, because
Yeah.
my camera is very blurred at the moment, and I don't know what.
I am not unhappy with that. Yeah. You only that both.
Yeah, I don't understand why.
Even I can look beautiful sometimes.
Does anyone have an idea why it's not getting?
I broke it probably. It's obvious.
So, closer or you listen from the blackboard?
I'm sorry, just. Usually automatic, zooming in and out. And
Maybe if you would want it a little bit downwards, because maybe it's confused with the upper board.
Yeah.
I knew it, the technology didn't work. Yeah, to stick to one board.
Introducing technology.
Yeah.
Camera.
Yes, sliding objects for me.
Okay, yeah, now it's almost even.
Okay. Okay, go ahead.
It's
Yeah.
your first word. I mean,
But because
we can postpone,
maybe
you know.
I don't know.
It's your person, you put the camera out of focus.
I think you never saw me like me and the camera alone. You cannot prove that. Move it slightly.
Well, same as before. Just one. You see, kind of closer, like noise. Do you want to try to come closer and then go
Okay.
back to the black one?
I can really break it.
Okay,
And now I slowly go back.
okay. Let's see if it's stable. No, okay. Let's go.
What a time walk. Don't move. That might be difficult. So, where were we? Okay, let's again assume that we have two exact random algebroid E1 and E2 that are like unrelated. There's a relation R between E1 and E2 supported on C, which is the submovement of 1 cross M2. So, and let me assume that both of them are endowed with the Ki transverse generalized metric. Okay, so when R is a transverse generalized isometry? Well, when the following happens, which is for any B, B, C, we'll just consider R of the intersection with curly W plus the direct sum curly W minus P equals to the other thing. So R3 intersection curly W plus P direct sum R3 intersection this guy where these are defined if there exists W tilde I plus such that this is verified. Okay, so if I have W tilde I plus splittings of these two short exact sequence such that this is verified, then I can write define. Then I have to verify this equation to say that R is a transverse generalized isometry, where I didn't tell you who are W plus and W minus. They're just the obvious guys you can think of. Just going to be given by W1 plus cross W2 plus, where the minus signs are just defined by taking the first. Okay. Sorry, W minus actually should be not careful. W minus is just given by W per mod, which is pretty much the same thing that will be, but it should be okay. Okay. So these are the conditions I want, and as you can see, since this is the definition, sorry, I missed like the most important part, which is the thing. Otherwise, all the spiel that's done before that would have been absolutely meaningless. As you can see, since curly W is defined in this way, what I'm really preserving is not the whole of W, but only a subbundle of it. In particular, I'm not necessarily preserving K. I could have the K is preserved with this relation, but it's not one of the requirements of making. Precisely for the, well, if you go back to that example, one motivation could be that. If you go back to that example, you have two foliated, the Courant algebroids over foliated manifolds. If I actually choose to preserve K, I would also introduce a notion of relation that preserves the foliation. I mean, or like maps one foliation to the other. I do not want to do that. It might be too restrictive. And so you can guess if I have to take quotients with respect to those two foliations, and for instance, consider like the relation coming from an isomorphism of Courant algebroids, supported, covering the diffeomorphism. This would mean that diffeomorphism would descend to the quotient, and then the quotient manifold would be diffeomorphic, which means if I want to do something slightly trickier, like T-duality, I would always have the same topology on both manifolds, and I don't do that as a motivation. So I don't want to preserve the topology of this thing. I need something that is slightly more general. And I think even if you like possibly T-duality, I think you can't find motivation in there, because in the end, when you take two different quotients with respect to two different Lagrangian subgroups of a Lie group, well, you don't have that. The orbits of those two groups are not into each other for any reason. They're not preserved. And that's why you end up having groups of different topology, which are relevant to T-duality, I'd say. So this is the definition I'm giving you. And since I give you this definition, I can also give you like, a sort of the result that I've been sort of spamming throughout the talk yesterday, which is the following, let's call it a proposition, which is consider the reduction relation supportable. Okay, then, and suppose that V plus is a generalized metric for the reduced Courant algebra. Okay, then there exists a unique transverse K transverse generalized metric W E such that QK is a transverse generalized. Okay, so this is one bit of information. If you start from the bottom, you can pretty much pull, what I'm telling you is that you can pretty much pull back what you have at the bottom to the top in such a way that QK is a transverse generalized, which it's something that I'm going to need in the future. But there's also a converse to this theorem. If you have a K transverse generalized isometry, fitting again with this picture of a reduction, then V plus, defined as pretty much sharp of W, is a generalized metric on E such that K is a transverse generalized So you also have the obvious construction.
I mean, W is transverse generalized metric and isometry.
Sorry.
You said that W is
A
a transverse generalized metric.
Yes, absolutely right. Yeah, this is a transverse generalized metric, yes.
Okay.
And then you have the obvious construction. So the obvious construction you have using that map, projecting down your subbundle, actually works. And this is a generalized metric. This is a proper generalized metric, not a transverse one, not the generalized. And I'm going to need, again, I'm going to need this resolver, which is pretty much based, again, on the fact that you can construct those famous splittings that I was talking about. Plus, it's also useful, it really heavily relies on the fact that W is spanned by basic sections, because that kind of allows you to have well-behaved spanning sections on both E-red and E.
How do you define glass? Is it defined by sharp on W or?
Yeah, it's just sharp on W and just the image of that. Since it's natural, yeah. Technically, yeah, it's not a musical isomorphism.
Let's put it that way.
So it's the nature of W. And yeah, I don't think I should tell you more about it. This because it's not that bad, but it's quite long. It's pointless for me. I should probably spend a few words about the composition of these objects, but just a few words because it's technical. I mean, again, as you can imagine, if you compose two transverse generalized isometries as relations, you do not end up having a transverse generalized isometry. It just happens if some regularity conditions happen to be verified, like the supporting submanifold need to have clean intersection. You need the relations themselves to intersect cleanly in some sense that they are defined. Plus, one more condition is that if you consider some special subbundles defined by two relations you want to compose, well, they have to have a non-zero arc. But I'm not going to tell you anything more about that because it might just get long and tricky, and we don't want to go that way. So, in any case, you can compose them, provided that you can find some sort of regular enough relations. So yeah, fair enough. So all the technical stuff I want to show you is kind of there. Now I want to introduce what's the idea behind using these guys for T-duality. What do I mean by T-duality in a way? So again, the basic idea would be to have, say, two Courant algebroids endowed with some geometric structure that, I mean, in my opinion, since the title says so, needs to be, related by some relation. How do I construct that relation? That's the whole point. So I will start with this picture, which is pretty much given by, again, I'll just give you the picture. So I will assume that I have two Courant algebroids over two different base manifolds, not necessarily the same, such that you can define a relation, such that the reduction is vertical. Okay, so I'm going to have this is going to be in red 1, this is going to be in red 2. And what I want to be related, so the Courant algebroids that I want to be related, they're defined T-duality, are these two guys on the bottom. These two guys can be isomorphic, so I'm just going to consider the relation given by the graph of phi, where phi is a algebroid isomorphism covering phi, which is just going to be the diffeomorphism between M1 and M2. Okay, this is sort of the most general setting I can think of for T-duality. In some cases, this phi is going to be what is called the B transformation. In some cases, it can just be the identity, whatever it is. But that's the only thing I can require at this stage. I just want them to be isomorphic. I just want this to be. I just want this guy to be. The whole picture, like to be well defined. And what I want to find are conditions for these two guys to be for a relation to exist. What does it mean? It means that I have to consider this relation. Sorry. The transpose, this guy, QK1 transpose, so that I can compose these guys and obtain a relation here. Just using the relation, I don't know. It's not necessarily going to be that anything. And this relation here, five, is going to be the relation that would call for these two Courant algebroids to be, for them to be topologically T-dual, for instance, because they're just defining, topological terms of my sigma model. They're, well, naming like up for discussion because, well, for topological duality, like in the literature, you can find a lot of references that are not really talking about this picture, but we don't have maybe a better guess. But in any case, this picture should tell you when things are right for T-duality to happen. Okay, so when you can actually start introducing some data. So when is R5 actually, when you can actually construct R5? When is this relation where I didn't tell you, so we didn't stress hard enough that R5 is given by the following. So R5 is just going to be given by this. Just the opposite. You compose with graph R5, compose with K1 transpose. Okay, what is this relation? Well, we have a theorem proposition. Well, this is supported, sorry. We also say that this is supported on by 1 and 1. 5 and 9. 1, 2, 3. Where need to in. So this is the submanifold on which this relation is supported. And well, so we have this following, let's say, theorem. R5 is relation if -1 of K2 intersect with K1 as constant. This is the only condition that you need to satisfy for this guy to be a relation. This is actually not the commutative either. Let me stress that as well. But you can form the relation. So when this happens, for this talk, I'm going to say that E1, E-res1, and E2, and E-res2 are topologically T-dual, because I don't have a better name for it. As I didn't have a better name for transverse generalized isometry, because, well, I'm not preserving the bit that the metrics are transverse with respect. But anyways, I call it transverse generalized isometry. So this is the thing I have. This is the picture I would like to have, at least the starting picture for T-duality. Of course, I need to introduce geometric metrics, generalized metrics, or transverse generalized metrics for them to give you a well-defined T-duality. But I also want to stress something else. In particular, what happens to the base manifold of these vector bundles? Because something funny might come up, which is going to be needed in the future. And I'm talking about, so for instance, what happens when you can actually draw this whole picture? You have, for instance, that the base manifold of E1 can be endowed with the following surjective submersions that are given by 1 to 1. And yeah, just the pullback of 1 by 2. Okay, and there are two surjective submersions. If you are familiar with the notion of bisubmersion of Hausdorff-Morita equivalent foliations, this picture should start looking familiar. Because I have two surjective submersions. If I can actually endow Q1 and Q2 with some foliation for some reason, then they're going to end up being like in the same equivalence class of Fourier manifolds, which is, as I was saying, the class of Hausdorff-Morita equivalent Fourier manifolds. Why do I want to do that? Because, well, in a way, in order to have a well-defined notion of T-duality, I need some objects that are going to define invariants for the tensors I'm going to define on E-red1 and E-red2. And those foliations, if I impose one more condition, are going to give me that kind of, and they're going to define me like, with respect to what my tensors are going to be invariant. So, in particular, what happens? If you actually end up having that these two vibrations actually have connected fibers, and you impose that the following holds true, which is sections of the kernel of Z1 star sections of star actually ends up being a section of kernel star, then if this holds, then you have that Q1 is foliated by a foliation I'm going to call, or how do I want to call it? I don't know. Well, you actually end up having this. There is a result due to Zambon, Andronidatis, Cantalis, all these people that says, that Q1 and Q2 inherit foliations, because you're pretty much saying here that M1 is foliated because of this condition. And actually so we have that Q1 and Q2 inherit foliations. Here I should actually, in my specific case, I should always say that this in back or something. You actually have foliation, say, one that you with one between F2, such that by 1 star minus 1 of 1 actually equals to 5 star R by 2 star minus 1 of F2, which equals to why did I put the star? I don't need the star here, which actually equals to the whole foliation in the iteration F1 and F. Okay? So this is pretty much the picture that they give you. In particular, you might notice that F1 and F2 are not necessarily regular foliations at this stage. Because, well, simply the intersection of these two guys can be anything. So when you're actually going to project them down, you can end up having something very regular. But actually, the notion of bitwise submersion in algebroid regular foliation is defined for singular foliations. So in principle, these two foliations are singular. But if you actually use this theorem and you impose this condition, a byproduct of this condition is that the intersection of the kernel of the differential of this map and the kernel of this differential of this map actually have constant rank, which means that F1 reduced and F2 reduced are going to be singular regular foliations. Okay, so I end up having what I'm going to call the sub-bundles of TQ1 and TQ2, which are going to be given by P. So these are sub-bundles of P. I'm going to call them in the future. This thing are going to be called bundles of T-duality directions, because they will represent the invariance of the metrics I'm going to put here and here. Okay. Maybe a comment here is worth about why this condition. I compare this condition to for instance, like to the case of Poisson-Lie T-duality. I compare this sort of general invariance, or the potential general invariance with respect to this big subbundle here, to the fact that you have a G equivalent action. Okay, so that would be replacing that condition that I don't have in this case, and I'm just going to impose some sort of different condition on having a big foliation actually inducing two small ones here. If you think about it, in Poisson-Lie T-duality, when you have just G equivalent action, you just have your manifold diameter, which is going to end up with the principal G action, and then you take H to be a H1, and H prime to be two closed subgroups of G, so that you end up having two well-defined quotients. But you also have, let's say, curly B, the quotient with respect to the action G, and you can close this diagram because, well, after the G action, the G action increases an action in Q1, then which is a quotient up again, and you can have this diagram. Here, you can complete the diagram. Here, I don't have that, but I want a similar notion, which is pretty much going to be given by the story I just told you. Okay, I might impose extra conditions, like if these guys here, if these foliations have smooth quotient, I'm going to end up having the same picture with fibered manifolds. I'm not going to do it. But as you can see, I'm trying to mirror a bit what happens in that case, provided some differences. So this is like the motivating bit for the next definitions, pretty much, because I want to again introduce the notion of T-duality directions. This one. Now I need to introduce some invariance conditions for the metrics on the reduced quantity algebroids with respect to PI. Okay. Did the camera go crazy again?
No, no.
Okay.
So just to get some information, there's this condition on the bracket of the sections.
Yeah.
For this equivalence.
Yeah, this is just a Libra, not Courant.
Yeah. So is this analogous to like Marotta equivalence of Boston manifolds? There's something similar that relates like the syntactic.
I'm fairly sure there is. I just don't remember it right now, top of my head. But for instance, you could an easy example to see how this is verified is when you have that M1 is endowed with the group action that is given by the product of two Lie groups. Okay. Then in that case, this condition, I mean, yeah, you just have to verify that, like, you know, the let's say the tangent bound to the orbits of these group actions satisfy this. But in that case, since the intersection of those orbits is clearly zero because you just have the product of any two Lie groups, then this equation is, like, you know, automatically verified. Or like, for instance, same thing, if you consider a group action by a Drinfeld double, like a classical Drinfeld double, then in that case, again, you have the intersection of your two induced Lie groups to bit zero, and then this equation is for free. You get it for free. And it's actually going to will give you, like, you know, this big foliation, just the orbits of the action of the Drinfeld double on the manifold. Okay. But to be fair, we didn't look at potential relations with Boston-Lie duality, for instance, like, you know, in depth. But so far, it's just an analogy. So, more definitions. In particular, like, you know, let me recall this so that whenever you have an exact algebroid, you have this short exact sequence. In particular, whenever you have splitting sigma of your short exact sequence, which is maximally isotropic, with respect to the periodic E, then you have an induced back splitting sigma star, which is pretty much given similarly to the definition of rho star by using the transpose of sigma and one of the musical isomorphisms induced by the non-general periodic here. Okay, so let me define again definition. So suppose that we have in this case, I'm going to suppose that I'm working on the red, and I choose a generalized metric on the reduced Courant algebroid. So I'm assuming that the reduction procedure works. Okay, and I assume that there exists a splitting sigma 1 that is adapted. Now, I obtain a splitting sigma red of 0. Okay. Sigma 1 splitting of E, so it's adapted in the sense that I defined last time. So I end up having a splitting sigma of the sigma 1 reduced of the reduced Courant algebroid. And then I say that V1 is V1 is D1 invariant, where D1 is this guy. My T-duality directions if the following holds. So yeah, the sigma 1 minus rho 1 star reduced of sigma 1 star bracket sigma 1 rho 1 1. I hope that the brackets are closed. The sections of E1. Section V1 for any one section of E1 and for any section of E1. Okay. Why? What does it mean? It's actually more straightforward than it looks. because in the end, this condition is just telling you one thing. Remember that in the split case, so when you have Tm direct sum T star n, V1 is simply given by the graph of a metric and a two-form. Okay, metric on Q1 in this case and a two-form on Q1. This condition, when you're in this case, and Q1 is foliated like innately, it just tells you that stupid. Let me say it's a silly condition, but why am I doing this? Guy is nothing but the representative of the Chevera class for. Sorry, I am. Sorry, this would be. This is nothing but the representative of the Chevera class in this case for my exact algebroid. I just want to take it out because I don't want it to be influenced by the invariance condition. I want it to be purely defined on the generator. And since I don't have any better way to do it, well, I'll basically do it by imposing this condition. And this is actually motivating why these DEI are called again T-duality directions, because in physics sometimes you start like from isometries of the metric on the background tensors for the starting Courant algebroid. In my case would be that E red one, and they're going to be playing crucial in the future. Okay, so this is the motivation behind this definition, and I have one last definition as well as. That is the existence of compatible splittings for my Courant algebroids E1 and E2. Okay, as you can guess, when we have isomorphic Courant algebroids, also their short exact sequence are going to be isomorphic. So in particular, what I mean is that I start from E2. Start again. It's going to be row 2, Tm2. Minus 1, row 1, T1, okay, and this is just, well, the differential of the diffeomorphism phi that is covered by capital Phi. Well, then, what happens when I have an adapted splitting of this guy? So sigma 2. Sigma 2 is adaptive splitting with respect to the whole reduction procedure, in the sense that that's unbounded lines. Does this sigma 2 induces an adaptive splitting on E1? No, not in general. It just doesn't happen. You just end up having a different splitting sigma 1. But what happens if you have an adaptive splitting sigma 1? Then are there like any compatibility conditions between an adapted splitting and the splitting induced by adapted splitting? This is what I'm going to define. So I'm going to say that we show that sigma 1 and sigma 2 compatible splittings if we have the following condition: sigma 1 and sigma 1 prime of x with E1. This time the bracket is going to be 1. Actually, I should have said that. Instead of always using this, I should have said this is the bracket on E1. But in this case, there was no possible confusion. In this case, there is. Just going to be by row 1 star, sigma 1 star. Again, of sigma 1 x, sigma 1 of row 1. Where frame x in M1 and E of E1. Okay. So this is my compatibility condition for these two spectrums. Maybe I can motivate this somehow. How do I do it? I can do it in this way. Let me again consider the split case, which I just have the M1 direct sum T7. Okay, So one splitting for this guy is just going to be the projection on TM1. The dumbest thing you can do. Okay, sorry. Yeah, it's sorry. The projection is the anchor. You're just going to find like the inclusion of TM1 in this. It's just it represents the splitting of this thing, which is adapted to the actual reduction procedure if you do it in the split case. What happens if you have that isomorphism? Well, an isomorphism in this case can always be written as this: phi star plus phi minus phi star composed with a B transformation, where this is just the exponential of B, a two-fold. You can always do that. This is an isomorphism going from TM1 P star M1 to TM2 P star. Okay, so it's always phi, if you're morphism between the base particles, and B is just a. What happens here? So if you actually choose on TM2 direct sum T star M2, the splitting that I told you about, so just the inclusion of TM2 in here, that is an adapted splitting to the reduction procedure. But if you project it down after taking this, you're going to end up that splitting induces a splitting of TM1 that is given by the inclusion of TM1 with a B transformation of the inclusion of TM1. So what you want to do, you want to B transform it back by this B transformation and get the original one in a way. So what I'm saying is this, that the equation here is telling you that sigma 1 in this specific case minus sigma 1 prime of x actually does nothing but I of x of b. And so you're imposing condition on how b should be behaved, so how the difference of these two splittings should behave, right? And what does it mean? Well, where x here is, it just means in the end that, sorry, actually here I made a mistake in the definition, because this is not just a section of TM1, it's a more specific section, which is rho of phi minus 1. This is why it's important. Because then when you want to change the splitting back, the condition that I'm imposing is just telling you it's just telling you that if I impose this condition, I end up having that L of x of b equals to 0 for any x that is pretty much in phi star t of 2. You have to do this again, the foliation that produces M2. Okay, so this equation that is actually fixing the splittings is just an invariant, ends up being in the split case just an invariance condition on B. Okay, which is pretty much saying that B is not just invariant, it has to be invariant with respect to somehow F2. Okay. Well, this was tough. But yeah, I guess at this point I'm ready to state like the main result. I have all the ingredients I need. Maybe I should have done it the other way around. You can forgive me. Well, at this point, I'm ready to state the main result that we have, which is the following. There we go. Put it here. Let's write about it. So let me suppose that E1 and E2 are exact random admissibles that satisfy the reduction picture that I don't have anymore because I canceled it. Awesome. So pretty much they satisfy this. You can't for this. By the reduction procedure.
You can or you cannot.
You can. This is what I want. This
Okay.
is the starting point. This is the sort of rightness condition for this whole procedure. So I'm assuming that all the reductions are can be done. Everything can be done with respect to K1 and K2, which are isotropic subbundles. That's important. Then I assume again, the theorem that I have here that will satisfy pretty much that picture can be drawn. I assume that the condition, this one, the bisubmersion condition is verified. So I have a bisubmersion. I assume that E red 1 is endowed with a E red 1, this guy is endowed with D1 invariant generalized metric, where D1 comes from the bisubmersion condition. And what else do I assume? Well, I assume that there exists sigma 1 and sigma 2 compatible adapted splittings. Okay? Then the following three conditions are correct. One. Okay. So K2 per intersection 5 K1 is included in K2. Two, well, symmetric condition. K1 per intersection 5 minus 1 K2 is included in K1. 3. There exists a unique V2 in E2, generalized metric, such that R5 is a generalized. Okay, so what you can do is, if these conditions are verified, you can pick take a generalized metric here, pull it back, push it forward, push it down, and you get just one of them, such that R5 is a generalized distribution. Well, no, I'm not going to prove this because it takes quite a while, but you can do it. And pretty much all these invariance conditions are assuring that everything is well defined. The tricky bit to prove is actually the existence of the right splitting that allows you to do that. But you can find one. You can find one up to elements in K1 intersection 5 minus 1 K2, which is pretty much the bit that you want to quotient out all the time. So yeah, in particular, why do I care about this? Because if this happens, so if R5 is a generalized isometry, then I'm going to call my two Courant algebroids geometrically T-dual. Okay, so finally, I have a notion of T-duality that involves some geometric structures, which are like the generalized metrics. Okay, in particular, why did I spend a lot of time defining this guy, for instance? Well, because this guy allows me to pull back the metric from here, define a good notion of isometry up here without changing the assumption of isotropicity, and then push it forward. So I need this guy and the theorem that I just erased that was here about the fact that QK is a transverse isometry to be able to draw this picture as for this guy to be a generalized isometry. Okay, so for instance, what's the difference with, say, Poisson T-duality? In that case, what is very important, besides the fact that the actions are non-isotropic, is that you can rely on the existence of the reduction procedure on B as well. So you can actually define good generalized isometries here, and when you compose them, you actually end up having a good generalized isometry between these two guys. I don't have that, but I find like a way sort of escape route going from up top. So that's why this is slightly different. So yeah, this again is the main result. What does it mean in loser terms? For instance, like if you're looking at the split case, what does this mean? How do you end up finding finding things that are actually fitting that picture? It might be useful to discuss that a little bit. So let me try to give you a few words about it, because those conditions actually characterize quite a lot all the tensors you end up finding. So I told you already about the invariances of V, the D1 invariance along the T-duality directions that allow me to do that thing, because in the end, as you could see, D1 ends up being very closely related to TF2, right? To the second foliation. It's just the push forward of the second foliation in the end. But then we have some more conditions. For instance, how do I characterize my my Courant algebraic isomorphism phi? In the split case, for instance, so when you have T and my direct sum T star and I, and I'm considering again phi to be something like this. Well, I cannot say much about phi, but those conditions are telling me what happens to B. In particular, B will have one relevant component, which is pretty much the one that is in the following subbundle. This part one, I'm assuming that each mi is foliated by a phi as usual. Intersection if I start if I'm related TFT, wedge, and my later of T of 1 intersection if I start T star F2. Okay, and why is this relevant? Because this one restricted to this subbundle must be non-degenerate. In other words, TF1 intersection phi star of annihilator TF2 star is isomorphic to the annihilator of TF1 intersection phi star T star. Okay, so this is the important bit. A non-degeneracy condition actually appears in the so-called, the topological T-duality, the notion has been introduced by Bog, Matai, and other people. And actually, you see that when these two foliations have zero intersection, this pretty much says that B must be non-degenerate on, must represent an isomorphism between like TF1 and, between the vertical subbundles defining these two foliations. I'll tell you more about this, but when I get to the example, if I get to the example. So this is one condition. So the characterization, this theorem in the split case pretty much gives you one condition on B. Okay. We have also other condition that I already discussed about, so the invariance of the tensors, but that's characterizing the phi itself. So, in particular, the theorem that I just told you boils down to the following proposition in the split case, which says if x of b equals to 0, then, then the generalized isomorphism. What do I mean by this? G1 plus B1 is just going to be the graph of my generalized metric on TQ1 dot T star Q1 Q. So if I have a generalized metric that satisfies these invariant conditions for any x in section phi star F2, so this factor F2, yes. No, well, I should say these sections of B1 and for any x is in sections of phi star F2. Otherwise, I'm on the wrong boundary. So if I have invariance condition with respect to D1 on the base manifold Q1, and if I have invariance condition on M1 with respect to X section of the pullback of T star F2, of TF2, sorry, then I can find a generalized metric, a generalized isometry R phi, pretty much satisfying that, given by that theorem. Okay, this is just in the split case. It's just to probably give a sort of more quantitative picture of what was going on. Okay. I could also make like D1 might also be for T-duality directions, because B, since does this job, it's sort of like flipping elements in the push forward of the foliation TF2 with other elements that are not going to be quotient out in the other case. which is sort of like, if you look at it from the physics perspective, that's sort of like, what happens when you do the T-duality machinery by gauging signal models, whatever that is. But anyways, at this stage, I think I can close it with the example. Okay, I don't know how much time do I have.
I think it's.
If I have 5 minutes, I'll finish.
Yeah.
Give the T-duality picture, at least in the correspondence picture. Okay, so. In particular, one and two manifolds are called T-dual. Well, let me assume the following definition. This is given by Cavalcanti-Gualtieri, but I think it's based on other works by Bagnet, Matai, and more people. So Q1 and Q2 will be PK bundles, okay, endowed with H1 and H2, I mean, say HI. Torus bundles. I didn't say that, right?
Maybe
Just
not.
I just said bundles. Yeah. No, sorry. So closed. Such that we can consider the fiber manifold 1 cross over. So B is a common base for Q1 and Q2. You consider just the fiber product. So you can actually draw the following diagram. Q1, Q2. In particular, in my notation, this is going to be part by 2. Repeat, it's going to be usually 1 and part. Okay. So they're called T-dual. Q1 and Q2 endowed with this closed tree form called T-dual. Part by 1 start of H1 minus part by 2 start of H2 equals to some leap. So it is exact. Okay, for some 2 form on the fiber.
Okay, this B is not the B.
This B, that is the trick, right? This shouldn't be, in general, this is just, I might call it F, I might call it something else, but in the picture that I want to draw, again, my phi should end up just being a B transformation EB by this guy. And actually, here you get like, if I consider like the fibers of these things, and I'm going to call them T1, TIK, it's just a kernel of star. If I consider this, you have to assume one more condition. Cavalcanti-Gualtieri assumed that B as a map going from P1K tensor to K into R non-degenerate. Okay. As you can see, T1K and T2K have 0 intersection. If you look at the theorem that I told you about, if you have that HI are defining twisted Courant algebroids on both Q1 and Q2, and you actually pull them back, so actually you have an exact Courant algebroid on M with Chevreul class given by the pullback of HI. This is definitely reducible to Q1 easily. And then what do? You have to define a transformation, phi transformation, which is going to be given by any B transformation. If that thing is possible, so if you can draw that diagram, you end up having that B on this guy has to be non-degenerate. So this is a byproduct of the fact that you can draw that diagram when this is a generalized isometry. It just, you can do it only if this happens, which is part of their definition. So we're sorted. And then what do? Well, we need to, actually, this is one of the things. One thing you can easily show is that if Q1 and Q2 are T-dual in the sense of Cavalcanti-Gualtieri, then they are T-dual in the sense of the definition I gave you. Sorry, topologically T-dual in the sense of the definition I gave you. Okay, so the one view. It's actually not too hard to show. Then what else can you do? Well, this is probably the real result about this whole thing, which is the following proposition, which is, well, consider again TQ tangent Courant algebroids over Q1 and Q2 with this Chevreul class, respectively. Okay, we endow them with generalized metric V1 1 and V2. Okay, such that they're so. Let me suppose that that is possible. Then Q1 and Q2 are T-dual in the sense of Cavalcanti theory. Okay, you can show this. It's going to be the definition by Cavalcanti theory. So if this happens, so if that diagram can be done, then your Q1 and Q2 are T-dual in the sense of Cavalcanti theory. Conversely, if you have that this definition holds, and so def Q3 holds, plus there exists a generalized metric V1 in TQ1, then there exists a unique V2 and TQ2, such that R5 is a generalized. Okay. The story actually is not over because you can do more. This relation is actually helping you preventing using what they call the Fourier-Mukai transform. You don't have to do it, which is a sort of partly fiber integration over the submanifolds of these fibers here, because they're compact. Well, you can always do it. Or one time you end up integrating on one TK, and on the other one, you can just do it. And they define a map, which is actually given by the following. So you end up having a. This is defined by Cavalcanti theory by using this guy, by using the Fourier-Mukai transform. So the choice of B to be non-degenerate plus this hat just means like a horizontal lift. So a choice of connection for this guy. If you can choose that, if you have basically a choice of connection that is also fixed by B, that is also being non-degenerate, you can define this map. Well, what you actually end up showing is that R of phi, in this case it should be in R of E at minus B, is when you restrict it to TK invariant sections, give you exactly a C infinity B modular isomorphism of TK invariant sections of TQ1 and TQ2, which is actually exactly this guy. So the one that Cavalcanti theory defined. And you don't have to do any Fourier-Mukai transform, no integration on the fibers whatsoever. You just use B as additional structure to construct the fiber product and nothing more. One last thing, if you actually really are into physics, R phi, if you just write down R phi, the whole construction, the whole procedure, gives you something that's called Busher rules in physics. Literally, it just tells you how the metric B2 generalized metric should be done. And the components of this metric are known in physics because, well, they literally satisfy the Busher rules that are known to physics. And R phi just does that for you. So I think I can finish here. There are like more examples, but enough is enough.
Thank you very much.
I don't know. Just joking.
Okay, and just simple question. So if I take my Poisson T-duality scenario, and then I just forget about I have this B downstairs, right? So I just take my E1, E2 to be the same exact Courant algebroids, and phi to be identity or something.
Yes.
Or maybe B transformation probably.
Yeah,
Does it fit in this theorem? Does it satisfy the property?
we are looking at it because in the Poisson T-duality case, I think the fact that the reduction is non-isotropic or like can be non-isotropic is important. In this case, well, what we're trying to look at is like what happens when you have disconnected relations for non-isotropic foliations. I would like to show that you can do a foliated Poisson T-duality. Yes, that's the goal. I don't know yet. The feeling is that if you can modify the definition of basic sections to something like that. The reduction procedure should work anyways when K is non-isotropic. If you can modify basic sections like this, probably you have a chance that the whole picture fits. If you don't, then yeah.
But if you move out, you know, by this Lagrangian subgroup and everything, then it is isotropic.
It is true. Actually, yeah. One
If you
example.
go from this G equivalent or G equivalent one to
In fact, actually, yeah.
you cross whatever by this G.
It is.
isotropic.
I know. Actually, in particular, you know, I checked it only in the case of dreamfield doubles. In that case, it actually works. Because it's the obvious one, and it definitely works. So you can do the procedure starting from here and go up. So in that case, you can. You definitely can.
So you have a machinery how to take any generalized method. Oh, it has to be one invariant.
Yes, you need some invariance condition, otherwise it doesn't work. That's the, so yeah, it's still constrained, but I think that invariance is sort of physically just because, you know, when you look at the Godwin invariant, it's kind of, yeah, you have some isometry, which is sort of, you know, it's geometric, like it's sort of geometric-like picture, and you don't really know how it goes, and that should be the equivalent. That's the machine. Okay.
Another question? Maybe I would have one. Much similar question, but if I'm not wrong, once you have generalized isometry, you implicitly think of some kind of algebroid relation.
Yeah.
So there's probably some more or less equivalent assumption that this intersection, as you wrote, this intersection of right image K2 and K3 is confound is somehow implicitly imposed in one or two, or is it?
No, I cannot. Well, you kind of have to find. Well, let's say that condition kind of constrains a bit the isomorphism you can choose. It's not like it's kind of telling you something about the isomorphism and the reduction procedure you can do. For instance, I think the example here is telling you that. Because when in the examples case, you have that phi is just EB, right? So that condition is telling you that B has to be, that constant rank condition is equivalent to having B non-degenerate on this subbundle, okay? Which is pretty much the same condition that, again, can be what you defined, but it's a constraint that you get for the machinery that you know to be working, okay? So that's one of the things. And then what you have in condition you for like the various ones.
I have a question about
When you start from here into CM2, take sigma 2. This is an adaptive splitting. Let me go to the isomorphic Courant algebroid. Then this splitting induces a splitting of this one. Okay. This induced splitting is the one I call sigma 1 prime. So sigma 2 appears here because it's just coming from this commutative diagram. And this one is not adapted. In principle, it's whatever. it's something else. But you can fix. You can fix it like, you know, in the right way. And in the split case, this is just a fix by B transformation. It's exactly the B transformation that defines phi.
There's no other question. So some question online, please. So if not, I'd like to thank you again for a nice lecture. And
Thank you.
unofficial, the open.
Among friends.